We are using the traditional method to test the hypothesis about the difference between two means. It says the U.S. Census Bureau reports that the average commuting times for citizens in Baltimore and in Miami is approximately 29 minutes. To see if their commuting times appear to be any different in the winter time, they took a sample of 40 drivers from each city, and they found their average commuting time, which you can see in the table. And then at an alpha of 0.05, they want to know if it can be concluded that the commuting times are different in the winter. So the table shows our two sample sizes, and we are going to call this Miami number 1 and Baltimore number 2. And so this will be N1, this will be N2. Those are the two sample sizes. The sample mean, this will be X bar 1, and this will be X bar 2. Those are the two sample means. And the standard deviation, this will be standard deviation 1, standard deviation 2. Also notice that this is a population standard deviation here, so we'll be using the Z table because of that. Let's get the hypotheses. The equal sign always goes in the null, so the first hypothesis is that there's no difference between the two cities in the winter, and no difference would mean that they're equal to each other, or you could write it that if you took the difference it would be 0. We usually write it this way, but this is equivalent to it here. The alternative would be that there is a difference, they're not equal to each other, and I believe this problem is claiming that. They're wanting you to test to see if there is some kind of difference in the winter time. This is a two-tailed test because of the equal, not equal to, so you're going to have two critical values, and there'll be two critical regions. The two tail regions will be the critical regions. The alpha of 05 gets split into the two tails, and so this tail area is half of 05, and this tail area is half of 05. It's easiest to find this Z first by looking this area up. I think if you go to your Z table, you'll get negative 1.96, and then the corresponding one is the positive 1.96. The test value is found by using the formula, and the formula looks like this. So the first X bar is from your first city, and it was the first sample mean, 28.5, minus the second city sample mean, 35.2. We don't need to put this part in here because it's a 0 from up here. You can see it's a 0. You could put a minus 0 back here, but I'm not going to. Like, you could write minus 0. I just ignore it. The standard deviations. The first standard deviation for the first city is 7.2. You're going to square that. Then you're going to divide it by your sample size. The other standard deviation was 9.1. You're going to square that, divide it by the sample size. You'll add those two results together and then take the square root of it. Maybe a little tricky to get it in your calculator, but when I do, I'm getting negative 3.65. That's my test value, negative 3.65. Then you want to watch where that test value is on this picture. It looks like it's over in here. You know, it's to the left of negative 1.96, so it's clearly in the critical, the left critical region. And so whenever a test value is in a critical region, you reject the null hypothesis. So we're going to reject the null hypothesis because the test value, the negative 3.65, is in the left critical region. So we're rejecting the null hypothesis. I'm going to slide up and have you look at the hypotheses. So we're actually rejecting this null hypothesis, which means this alternative is true and the claim is attached to that. So it means the claim is also true, and the claim is that the commuting times are different in the winter. So we're going to come down here and you'll say there is enough evidence to support the claim that commuting times are different in the winter. Even though they aren't other times of the year, they are different in the winter according to the data.